On 1st January 1894, a man was born in this house in North Calcutta who would change the face of physics and whose name would forever be associated with that of Albert Einstein, Satyendranath Bose. His parents, Surendranath and Amodini Devi, belonged to the middle-class educated Bengali society. This is Bose's native place, where there is now a primary school in his memory. Bose first went to normal school and then to the Hindu school. He passed his entrance examination in 1909. While in school, his mathematics teacher, Upendra Bakshi, once gave him 110 out of 100 in a maths test and predicted that one day Satyen would be a great mathematician like Laplace and Cauchy. The year 1905, when Satyen was only 11, was a turning point in the history of Bengal. Lord Curzon partitioned Bengal on 16th October, triggering widespread protests. It left a lasting impression on the young boy. After school, Satyendranath went to Presidency College, where he met his lifelong friends Meghnad Saha, Gyan Chandra Ghosh, Prasant Chandra Mahalanobis, Gyanendranath Mukherjee, and Nikhil Ranjan Sen. He had distinguished teachers like Jagadish Chandra Bose and Prafulla Chandra Ray. He stood first in the BSc Honours in 1913 and the MSc examination in Mixed Mathematics in 1915. His MSc mark sheet has become legendary. His friend Meghnad Saha, who would revolutionize astrophysics soon, stood second. He married in 1914. In 1917, Satyendranath and Meghnad were recruited by Sir Ashutosh Mukherjee, the Vice-Chancellor of Calcutta University, as lecturers in physics and applied mathematics in the newly established University College of Science. They were the first in the world to translate Einstein's papers on relativity from German to English, and these were published in 1919 by Calcutta University as a book titled The Principle of Relativity, with a historical introduction by P.C. Mahalanobis. Bose's first scientific papers were published, some in collaboration with his friend Meghnad Saha, during the years 1918 and 1920. The University of Dhaka, established by the British government, started functioning in 1921. Bose joined Dhaka University the same year as reader in physics with his friend Gyan Chandra Ghosh as a colleague in chemistry. This is the house in Dhaka, now demolished, where he lived.
There was a crisis in physics towards the end of the 19th century and the beginning of the 20th. It came about through careful studies of what's called black body radiation. Now, a black body is something that absorbs all the energy that falls on it. When you heat a body, it first becomes red hot and then eventually white hot, when the light coming out of it has all the colors of the rainbow in it in equal measure. Each color carries a certain amount of energy. These curves show us how the energy is distributed among the colors. This one is the spectrum when the body is red hot. The dominant energy is emitted in the red color. As you increase the temperature, the maximum shifts towards the ultraviolet. The problem is that classical theory predicts that a black body should radiate infinite energy from the ultraviolet region. That is, of course, absurd. And the experimental curves actually turn down in the ultraviolet region. So there is a clear contradiction with the established classical theory. This came to be known as the ultraviolet catastrophe. Towards the end of the 19th century, Max Planck of Germany wrote down the formula that correctly describes these experimental curves. It was an inspired guess. It had two parts. The first part follows from classical physics, but not the second. It is the second part that makes the curves go down and avoids the ultraviolet catastrophe. The question that arose was, what sort of physics would give rise to this second factor? Planck suggested that the second factor implies that energy cannot be absorbed or emitted by a body unless it comes in packets of a minimum amount he called a quantum. So a body is like a high-rise building. If you want to throw a ball into a flat on the first floor, you have to give it a minimum amount of energy. Otherwise, it won't reach the first floor. If you want to throw it to the second floor, you have to give it twice that minimum energy, and so on. Obviously, it follows that a ball falling from the fifth floor, say, to the ground will have 5 times the minimum energy, and so on. From this simple assumption, Planck managed to derive the second factor. That was the first step in the quantum revolution. In 1905, Einstein introduced the second step in this revolution. Through a remarkable analysis of the Planck formula, he showed that light must travel both as waves and as a stream of point-like particles, like tiny bullets. We call them photons now. He showed that it immediately gives a very nice explanation of the photoelectric effect. When light falls on metals, electrons are immediately emitted. Their number depends on the brightness of the light, but their energy increases as the light becomes more and more blue. This cannot be explained by classical wave theory. This was the beginning of the famous wave-particle duality. How do you make sense of that? Waves are spread out and interfere to produce patterns, whereas particles are point-like things that do not produce such patterns. Some scientists immediately pointed out that Einstein's bullet-like photons contradicted Planck's law. Now, this was shocking to Einstein. How can something that follows from Planck's law contradict it? So this was a crisis for Einstein's theory. This led to a number of attempts to give a more satisfactory derivation of Planck's law. Planck himself, Debye, Einstein, Pauli, and Einstein and Ehrenfest, all of them came up with their own derivations. This was the state of physics when Bose began to teach quantum theory in Dhaka University. He found it very difficult to teach because he found all these derivations suffered from a basic logical fallacy. Each derivation took the first factor from classical theory and gave different arguments to get the second factor. Soon, Bose came up with a derivation of the entire Planck formula from quantum theory, including the first factor. His derivation showed that photons were not bullet-like as Einstein had assumed, but somewhat diffuse, and that meant that they had to be counted differently from ordinary particles like bullets and billiard balls. That was the beginning of a new form of statistics, quantum statistics.
See, after he was able to give this new derivation of Planck's law, he sent his paper to a philosophical magazine in England, but they rejected his paper. So then he sent it to Einstein with a covering letter in which he explained what he had done and requested Einstein to have this paper published in some German journal. So Einstein was so impressed by this paper, he immediately translated the paper himself into German and got it published in a very famous German journal called Zeitschrift für Physik. And he added a footnote in which he said that he considered Bose's counting a very important step forward and that he would show himself in future publications how Bose's method of counting was applicable to gases. And that was the beginning of what is called the quantum theory of gases.
Armed with Einstein's strong endorsement, Bose set sail for Paris later in 1924, where he stayed for 1 full year. Refused by Madame Curie, who assumed Bose did not know French well enough to work in her lab, he worked for 6 months with Prince Maurice de Broglie, the elder brother of Prince Louis de Broglie, who was then setting up his X-ray crystallography lab in an abandoned horse stable in his stately home.
Art of analyzing crystals using interaction of X-ray with crystalline materials is known as X-ray crystallography. Okay? So, Professor S.N. Bose made remarkable contribution in the field of X-ray crystallographic research in India. Now, in those days, getting fund for scientific research was not an easy task. So, he designed his own X-ray crystallography laboratory and cameras himself using the help of mechanics in workshop in Dhaka University. He fabricated several X-ray diffraction cameras in Dhaka University and used them for analyzing clay minerals.
After 6 months, when Madame Curie was satisfied that Bose knew sufficient French to work in her lab, Bose worked in the world-famous Radium Institute in Paris for 6 months. This enabled Bose to do important work in chemistry on his return to Dhaka. After a year, Bose went to Berlin and met Albert Einstein for the first time in November 1925. He had many discussions with Einstein and became very friendly with several prominent scientists of the time. He returned to Dhaka in 1926 and was appointed a professor of physics. Back to his home ground, he set about developing the physics department and built a fine X-ray crystallography laboratory. He also worked in chemistry and wrote a number of papers during this period up to 1943. He became the dean of Dhaka University and the provost. In 1944, he became president of the Indian National Science Congress. In 1945, he returned to Calcutta University as the Khaira Professor of Physics. He had wide interests in music, painting, and literature. The poet Bishnudev, the famous painter Jamini Roy, and the famous singer Dilip Kumar Roy were his personal friends.
To understand Bose's method of counting, let's take these 3 little bowls and 2 identical balls. Now, in how many ways can I arrange these 2 balls in these 3 bowls? I can put both of them in this one, that's one arrangement, or in this one, that's 2 arrangements, or I can put them in the third one. So these are 3 possible arrangements. Or I could put one here and one here, that's the 4th arrangement, or this one here and that one there, or one here and one there, that's the 6th arrangement. Now these are the 6 possible arrangements of 2 balls in 3 bowls. But classical objects like these balls, they can be tracked. For example, if I have these 2 balls in this bowl and I interchange their position, then that's a new arrangement. So for every one of those 6 arrangements that I showed, you can get another arrangement by interchanging the balls. So there are 12 possibilities. However, Bose showed that in order to get Planck's law, one has to assume that interchanging balls like this does not produce a new arrangement. Now, what does that mean?
That means that unlike these balls whose path you can follow, these are classical balls, but photons have to be different. If you interchange two photons like this, it does not produce a new arrangement. What does that mean? That means that you cannot actually keep track of photons like this. And that is only possible if photons have some kind of a wave associated with them so that you cannot localize them. And these two photons have their waves overlapping, so you don't know where a particular photon is. And that is the basis of Bose statistics. Now, what is the difference between Bose statistics and Fermi-Dirac statistics? You see, in Bose statistics, you can put as many balls as you like in a particular bowl. It doesn't matter. But in Fermi-Dirac statistics, you cannot put more than one ball in each bowl. A Fermi-Dirac bowl cannot have more than one ball. Whereas photons, pions, kaons, W, Z, Higgs, they are like that. You can put as many as you like in one bowl. This is Bose statistics. This is why when you cool this down to a very, very low temperature, then they all become just one object. They lose their identity. You cannot say, this is this ball, that's that ball, that's that ball. No. In that state, all of them, hundreds and thousands of them, make one state. And that's called a Bose-Einstein condensate. There are only two classes of particles that make up matter and energy. Bosons, like photons, pions, kaons, W, Z, helium atoms, etc., and fermions, like protons, neutrons, quarks, electrons, muons, and so on. Many Nobel Prizes have been awarded, all based on this fundamental work which was done by Bose way back in 1924 in Dhaka.
Let us now go to the Tata Institute of Fundamental Research in Mumbai to see some of the labs there engaged in research on Bose-Einstein condensates, superfluidity, and superconductivity.
Welcome to the laser cooling laboratory of TIFR. It is in this region with this magnetic field and the vacuum chambers where we slow down the atoms and trap them. However, to do this, we need a very, very elaborate setup of optical components through which we send laser light onto the atoms. And these components which you see here are meant to engineer the state of light, its polarization, frequency, and so on, such that the atoms can absorb this light very efficiently. The laser light itself is generated in these lasers here, which are sent through these optical components. The frequencies are adjusted, and eventually they go into the vacuum chamber and act on those atoms, push them, slow them down, and we are able to trap them. And with those trapped atoms, we produce the Bose-Einstein condensate.
So this is the device which is called the dilution refrigerator, which uses the principle of superfluid helium-4. Helium-4 is a neutral, has a neutral charge and no spin. It undergoes a superfluid transition at 2.1 Kelvin. And this superfluid transition is coming because of Bose condensation.
Bose-Einstein condensation happens only to bosons, particles with integer spin values. We cool this down by pouring liquid nitrogen onto the superconductor. The liquid nitrogen cools the ceramic material to about 190 degrees below zero. And then there can be a supercurrent in the system because the electrons first pair up and then become bosons, and they condense into a Bose-Einstein condensate, which can flow without resistance. And that flow of current provides a large magnetic field, and that is what is keeping the magnet with the gap floating.
In the 1960s, when the standard model of particle physics was being developed, there was a problem. The theory demanded that all the particles had to be massless, but then they would flow off with the speed of light and no solid matter would be formed. So there was a need for a new kind of particle which would give mass to all the other particles so that the universe could be formed. And that new particle had to be a boson. And it was named the Higgs boson after Peter Higgs of Edinburgh. After a long search, the Higgs boson was eventually discovered in July 2012 in the Large Hadron Collider at CERN.
Bose visited various parts of the world, presenting his research, and took active interest in the development of several national laboratories and institutes in India to lay a strong foundation of scientific research in the country. He was appointed the president and advisor of several national laboratories, like the National Physical Laboratory, the Central Glass and Ceramic Research Institute, the Indian Statistical Institute, the Saha Institute of Nuclear Physics, Asiatic Society, and many others. Bose met the great Indian poet Rabindranath Tagore several times. Tagore dedicated his only science book in Bengali, Vishwa Parichay, to Bose. Inspired by Tagore, he founded the Bongyo Bigyan Parishad in North Calcutta in 1948 for the dissemination of basic scientific knowledge among common people through their mother tongue.
আচার্য বসু 25 বছর আগে বিজ্ঞান পরিষদের প্রতিষ্ঠার সময় কি উদ্দেশ্য নিয়ে এর প্রতিষ্ঠা করেছিলেন?
তখন সবে আমরা স্বাধীন হয়েছি, কাজেই আমরা ভেবেছিলাম দেশের মধ্যে বিজ্ঞানের কথা প্রচার করা, দেশকে বিজ্ঞানের যে সমস্ত অবদান আছে সেসব জানানো, যাতে প্রতিদিনের কাজে তারা বিজ্ঞানের যা কলকারখানার বিষয়েতে তাদের প্রয়োজনীয়তা বুঝে নিজেদের কাজে লাগাতে পারে, এই রকমভাবে তাদের শিক্ষা দীক্ষা।
The eminent actor Bhanu Bandyopadhyay and Pramotesh Barua, a pioneer film personality of India, were students of S.N. Bose.
These bubbles are the bubbles of the thermal gas that is emanating down below in Earth, many thousands and thousands of feet below. So it's carrying the message of the belly of the Earth. Along that, helium is coming out. Question that has bothered us quite a bit: what is the source of the helium? Where is the helium coming from? Not God, it's Mother Earth. The genius of Satyendranath Bose was that, forget about this business of ailments, there's something far more exciting is happening, and that 1.8% of the natural gas coming out is helium. It's a noble gas, and it is effective for many reasons. But that doesn't prevent from people having bath. It's no contradiction. And that is the beginning of this saga. In the month of Boishakh, coming to with Samadacharya and Devashish Ghosh, when I just came back to Calcutta from England, and it was an extraordinary experience when Samadacharya in his own voice used to say, you know, the whole place is over helium. And because I said, by the time the gas went to Bombay, the helium already evaporated. And then he found out from Germany there is helium here, and the story started.
He was awarded the Padma Vibhushan in 1954. The same year, he was nominated a member of the Rajya Sabha. On his retirement from Calcutta University in 1956, he was appointed Vice-Chancellor of Vishwabharati. In 1958, he was elected a Fellow of the Royal Society, London. In 1959, he was made the National Professor of Physics. With an office in the Indian Association for the Cultivation of Science, Bose lived a very simple life with his family, friends, and students. His 80th birthday was celebrated in a grand manner by many children and celebrities. He passed away the next month, creating a void in Indian science which would be difficult to fill. As a mark of respect, the Dhaka University in Bangladesh has set up a Bose Center with a museum which contains his famous correspondences with Albert Einstein, as well as some other personal belongings. After the creation of Bangladesh, the Bangladesh government made Professor Bose a friend of their liberation war. After his demise, the government of India established the S.N. Bose National Center for Basic Sciences in Kolkata in his memory. Many of his personal belongings have been gifted by his family to the archives in the S.N. Bose National Center for Basic Sciences in Kolkata and the Mongyo Bigyan Porishad. Towards the end of his life, he would often return to calculating a long series of numbers whose meaning eludes everyone. Like Newton, an amazing mind was voyaging through strange seas of thought alone.